Good morning. We shall now discuss about the analysis of two-port network. The presentation consists of an introduction, RF components, passive and active components, two-port network, multi-port network, elements of Z matrix impedance, that is impedance parameters, admittance parameters, ABCD parameters, scattering parameters. We shall now go in detail about the components in detail, and then the analysis of a two-port or multi-port network. Basically, for any electronics or communication, the technology consists of both circuit theory operation as well as field theory operation. Circuit theory deals with all the components and circuit level analysis, and then the processed signal energy is given to the field theory. Field theory does all radiation, propagation, transmission, and then the required output is taken at the outside. This is a reciprocal in the receiver. So let we have the discussion for the components, how it functions. And whenever we sit in front of a TV, or whenever the television or a stereo system or any electronic appliances is made on, and we believe that we call a alternating current to provide the power to operate the devices. So now it is essential to have a study of AC circuits by examining the characteristics of a circuit containing a source of electromagnetic force and one other circuit element. Could be a passive components, and a resistor, a capacitor, as well as a inductor. Initially, all the electronic components, including low frequency as well as high frequency, is broadly classified into two types. One is active devices, another one is passive devices. So now when we examine these components and when it is connected in the circuit, how it behaves, which are all the combination is giving the respective or a suitable result, So this is basically done in series as well as parallel configurations, both the passive as well as active elements. So now we know well the electromagnetic waves are composed of fluctuating electric and magnetic fields. When an electron is vibrating, this electron will vibrate only when it is excited. So naturally, in this active and passive components, the electrons are excited. Excited electrons are contributing for the vibration. So this vibration is contributing for the electromagnetic waves. And now the electromagnetic waves in the form of visible light enable us to view the world around us. For example, infrared waves warm our environment. Radio frequency waves carry our television and radio programs, as well as the information about processes in the core of our galaxy. And X-rays allow us to perceive structures hidden inside our bodies and study properties of distant and collapsed stars, which is all the long distance which we cannot see through our eyes. So that can be studied using these high energy X-rays. Light is key to our understanding of the universe, and we believe that electromagnetic wave travels at the speed of light. And the picture shows a sample of RF components. And the first one is a waveguide, a simple two-port waveguide. The next one is a high frequency resistor, and the next one is a high frequency capacitor, followed by high frequency inductor. To understand the analysis, please follow the cursor. Okay, let me talk about the passive and active components. Passive component in general, it does not contain any source that could add energy to the signal. Examples are resistors, capacitors, inductors. In simple, we can say passive components does not require any source. And coming to the active devices. Active devices is one in which an external energy source is contributing to the magnitude of one or more responses. In other words, the active devices are highly depending on the external source energy. The response is obtained only when there is a active external energy source that is connected to the active device. The examples could be transistors, diodes, and the respective diagrams, pictures are shown for our understanding. Next, so with the small introduction of RF components, let me go for the analysis of two-port network. So before we talk about the two-port network analysis in detail, let me have the discussion for the definition of what is a network, what is port, what is terminal, and all those stuffs. In general, a network can be basically classified into two types. One is a linear network. Another one is a non-linear network. A linear network can be defined like this, in which the parameters of resistance, inductance, and capacitance are constant with respect to current or voltage, and in which the voltage or current of sources is independent of or directly proportional to other voltage and currents or their derivatives in the network. In simple, a linear network is one which is depending on voltage and current source. If there is a change in voltage or current, the output will also contribute the same change in voltage or current. Input, whichever is connected to the source, based on that the output is obtained. That is known as linear. Okay, now any device definitely will have a terminal in order to give the connection to the source as well as to take the output from the device. So now a two-port network generally has four terminals in a circuit, in which the terminals are paired to form a input port and an output port. So naturally this is a four-terminal device. Okay, four-terminal devices is analyzed mainly for voltage and current, which the polarities are positive and negative. So this is for the input side, and this is the next one is for the output side. By looking at the diagram, we can understand that this has two terminals in the input as well as two terminals in the output. But if you have to define it in terms of port, then we have to say one input port and one output port. So this is known as two-port network. In the analysis pertaining to the low frequency, impedance parameters are the most common methodology to analyze the network which has two ports. So from the diagram we can understand voltages in the input is V1, voltage at the output is V2. So the contribution based on the Ohm's law, the expression at the input can be written as Z11 into I1 plus Z12 into I2. Z11 is the impedance at port 1. Z12 is the impedance at port 2 due to the contribution of port 1. I1 is the port 1 current, I2 is the port 2 current. And V2 is the voltage at port 2. That is written as Z21 into I1 plus Z22 into I2. Z21 is the impedance value that is obtained at port 1 with the help of port 2. And Z22 is the impedance at port 2, and the corresponding currents are I1 and I2. This is a general equation in Z parameters, and the impedance matrix is written as the output is V1 and V2, and the impedance value is Z11, Z12, Z21 and Z22, because it is a 2-port device which has 4 terminals. So naturally we have 4 parameters and the corresponding currents I1 and I2. So which is written in the form of V is equal to Z into I. And this can be extended to the multi-port network. If the concepts are brought simpler in 2-port, the same thing can be brought into the multi-port analysis too. In general, a multi-port network where the ports are defined as the access terminals or pair of lines at which a defined voltage or current is obtained. And the most important point that has to be kept in mind while doing the analysis of multi-port is equal and opposite currents are assumed on the 2 wires of a port. For example, if a network is having only 1 port, so the other end is not connected to the terminal. Here you have current 1, voltage 1, and the suffix is representing the respective port. And the next one is 2-port network, in which the analysis have been already done. And coming to the analysis of N port. N port has N number of current and voltage. You can analyze this 2-port as well as the multi-port networks by means of Z parameters, Y parameters, which are known as admittance parameter, as well as ABCD parameters. But these things are possible only at the low frequency analysis. If the network has to be analyzed for the high frequency circuits, then we have to go for the analysis of scattering parameters, which are denoted as S parameters. And now we will look at the elements of Z matrix, that is under Z parameters. And basically the elements are obtained in the analysis of open circuit as well as short circuit. Open circuit, the terminals are kept open. In short circuit, the terminals are connected with a load. Load is nothing but a resistor. Right. Now looking at the expression which we had already discussed for the Z parameters, V1 that is equal to Z11 into I1 plus Z12 into I2, V2 that is equal to Z21 into I1 plus Z22 into I2. If port 2 is open circuited, which means there is no current flowing in port 2. In that case, I2 current becomes 0. Under open circuit of port 2, current I2 becomes 0. Thereby, Z11, which is nothing but the impedance value at port 1, is written as the ratio of V1 by I1 by representing I2 is 0. How about the value of Z12? It is V2 by I2, assuming I2 is 0. Because the expression for Z is always taken as the ratio of V by I. Since this is based on the port analysis, we are defining the respective port is open circuited or short circuited in order to say that the current in the respective port is 0 or not. If port 1 is open circuited, which means current at port 1, I1 is 0. Z12, which is equal to V1 by I2, where I1 is 0. From the second expression, Z22 is taken as V2 by I2, where current at port 1, I1 is 0. So this is a simple analysis for Z parameters under open circuit. And if this has to be done for a n port network, then the corresponding port whichever is under open circuit has to be mentioned. And we have the analysis for series connected networks. So we can have lot more circuits and its component to be connected in series. So this expression shows that how a simple Z parameters are obtained in a series connected networks. So this is a series connected network. So accordingly, the expressions, matrix expression can be obtained like this: V1, V2. Because in a series connected network, the voltage at the input port as well as output port is going to be common. So they are two. This circuit has two devices which are connected in series. The total current V1 and V2 is obtained as V1A, V2A plus V1B, V2B, which is the voltage contributing by both device A and device B. Correspondingly, the respective impedance and current. So this is how the matrix will be written. Because current is going to be same in series circuit. Voltage is different, current is same. So the idea behind the series connected network, we have to understand current is same. Current in network A, current in network is same. Current in network B is same. Okay. Now considering a two-port network for admittance parameter. Admittance parameter is a complete inverse to impedance parameter. Admittance is generally represented as Y. So now here in this we will be finding out current 1 and 2 at the respective ports by taking the product of admittance and voltage. So Y11 into V1 plus Y12 into V2, that is equal to I1, that is the current at port 1. And the expression for current at port 2 is written as Y21 into V1 plus Y22 into V2. And in matrix form, this can be written as I1, I2. So these are the values that has to be found, which is written as the product of Y11, Y12, Y21, Y22. They are the admittance parameters. They are multiplied by voltage V1 and V2 at the respective ports, which is nothing but I is equal to Y into V. Admittance parameter can be analyzed as short circuited parameters. In the analysis of short circuited parameter, voltage becomes 0 because short circuited will have current as maximum, voltage as minimum. So by looking this expression, admittance at a respective port is written as I by V by short circuiting a particular port. In that port, voltage is going to be 0. And the same thing can be extended for n port network by taking up to n number of ports. So whatever the analysis, the respective port has to be short circuited. In nutshell, we have to remember like this: for impedance parameter or impedance parameter analysis, we have to do open circuit in the respective port. And in admittance parameter, for the admittance parameter analysis, we have to do short circuit the respective port. And this is again connecting n number of networks together. Since it is a admittance parameter, we need to connect it as parallel way. In parallel, voltage is going to be same. So likewise, the expression is written as I is equal to Y into V. So current contributed by device 1, current contributed by device 2, and voltage contributed by device A, voltage contributed by device B. So likewise the matrix is written like this. Remembering, under admittance parameter, the network is connected using parallel fashion. Okay, now let us discuss about a simple calculation how this open circuit and short circuit is understood in order for calculating the impedance. So look at this diagram which has a series and parallel combination. So this is a simple T circuit which is specified by resistor 1, resistor 2 and resistor 3, and it is connected by a current source, and the voltage produced at port 1 is V1 and the current due to the current source is I1. Look at the diagram. This is open at the other side terminals, which means this is open circuited. In open circuit, the current is 0. So resistor 2 has no current. Resistor 2 has no current. Thereby, the expression can be written as V1 is equal to I1 into the series combination of R1 and R3. The impedance value is obtained as V1 by I1, which is equal to R1 plus R3. In the second diagram, look at the second diagram. Now we wanted to find out voltage at port 2, assuming that it is short circuited. Assuming this is, that is the port 2 is short circuited. Now the expression for V2 is written as V1 into the parallel combination of R2 and R3. So now this is, current is allowed to flow in resistor 2. Current is allowed to flow in resistor 2. So this resistor R2 is in parallel combination with this R1 and R3. Hence the expression is written as V2 is equal to V1 into R3 by R1 plus R3, which can be rewritten as I1 into R3 plus R1. This is again series. This is series, that is parallel with this. So expression is written as I1 into R3. So the corresponding impedance value is going to be Z21, which is nothing but V2 by I2, which is equal to R3. And coming to the analysis of ABCD parameters, these ABCD parameters are slightly applicable for mid-frequency analysis. Here, the difference in voltage is considered. For example, considering a two-port network, the current is flowing in same direction, I1 and I2. Voltage and current in general in a two-port network is defined as I2 is proportional to V2 minus V1, V2 is proportional to I2 minus I1. This can be written as V1 proportional to V2 minus I2, I1 is proportional to V2 plus I2. Now introducing a coefficient, the matrix form for ABCD parameters is written as V1 and I1. The findings in ABCD parameters are voltage and current at the respective port, which is written as with the coefficients of A, B, C, D into V2 minus I2, because current is in the opposite direction as that of the current in port 1. Here it is mentioned with minus sign. And the determination of ABCD parameters are followed like this. In order to find out the coefficient of A, the corresponding other port must be open circuited. Hence, current at that port 2 is going to be 0, V1 by V2. And in order to find the next coefficient B, port 2 is short circuited. So voltage is made 0. Voltage at port 2 is 0, V1 by minus I2. The same thing is followed for finding the remaining coefficients C and D. Now we shall discuss about the ABCD matrix for series impedance. And in series impedance, the current direction is mentioned as that of the diagram. Current is taking the opposite direction. So now apply the same concept by terminating port 2 by means of open circuit as well as short circuit, and find out the value of the ABCD parameter for the given diagram. When it is made open circuit, current is 0. So one coefficient corresponding to current, that is I1 and minus I2, becomes 0. Thereby the matrix is written as 1, which is A, Z, that is B, C is 0, D is 1. And now the analysis of cascaded networks. Cascading is nothing but same networks, same devices are connected together. So instead of doing it in a series or parallel analysis, simply the devices can be cascaded. So the analysis is same as that of the ABCD parameter. And cascading network is analyzed using ABCD parameter. In that you can cascade n number of networks. So the diagram shows two networks are cascaded. So now V1 and I1 is written as the value pertaining to the network A. So V1 A, I1 A, and the corresponding ABCD parameters for A network, and V2 A, I2 dash A. The same thing is obtained for B also, because this A, look at the cursor, the output of network A is connected to the input of network B. Hence the expression is written as the product of ABCD coefficient at A and the product of ABCD coefficient at B. So the matrix for the cascaded network is written as like this: V1 I1, that is equal to ABCD, the product of A and B networks, into V2 I2 dash. And this is about the nice property that we can imply it for cascaded networks using ABCD parameter analysis. And so far what we have discussed is about the low frequency analysis and the parameters used for analyzing the low frequency circuits. And let us now go for the analysis of high frequency parameters. Before that, let we discuss about what are the problems in general we are facing when the same low frequency parameters are extended for analyzing the high frequency networks. First thing, in the low frequency analysis, the terminology for voltage and current is more dominating. Whereas in high frequency, instead of calling them as voltage and current, we take only the effects of voltage and current, hence we say it is a fields, electric field as well as magnetic fields. So the measurement and the corresponding or the supporting equipments for voltage and current in high frequency is not available. So non-availability of voltage and current measuring equipments in high frequency is difficult. And the other analysis is with respect to the short circuit and open circuit, because in high frequency short circuit or open circuit contributes standing wave ratios. As the frequency is getting increased, the effect of standing waves is going to be greater. So we cannot make analysis using short circuit and open circuit as that of in the low frequency circuits. So short and open circuit analysis are not easily achieved for wide range of frequency. Open circuit is much difficult. And the other important point is presence of active devices makes the circuit unstable for short and open circuit, because under high frequency the devices having the effect of standing wave ratios, which is contributed by the reflected waves. So the reflected waves are disturbing the devices under high frequency. This makes the high frequency devices more unstable. Next, at high frequency, physical length of the network is comparable to the wavelength of the signal transmitted. Hence the component size is much smaller. So that is again a very big reason so that it cannot get connected to the voltage or current measuring devices which are available in the low frequency, which is not compatible to that. In low frequency, the component sizes are very small, and it is much smaller than the wavelength of the transmitted signal, whereas in high frequency it is comparable to the wavelength of the transmitted signal. So these are the main reasons why low frequency parameter analysis cannot be extended for the high frequency parameter analysis. So in order to do the high frequency parameter analysis, we need to necessarily introduce a new concept called scattering or S parameters. This can be understood like this. So these scattering or S parameters are linearly related to the amplitudes of scattered. Scattered energy is nothing but reflected or transmitted waves, which of those incident waves. So there is a linear relationship identified in the transmitted signal as well as in the received or the reflected signal. So this is the idea or the concept that are used in scattering parameters. So with this idea, we will proceed how scattering parameters are implemented in the analysis of high frequency. At high frequency, as what we discussed, Z, Y, ABCD parameters are difficult to measure. Voltage and current are not always uniquely defined. Even if it is defined, we cannot make use of voltmeter and current meter to measure voltage and current in those devices. And another thing, we need to identify the open circuit and short circuit conditions. So the best way to measure high frequency components are using scattering parameters. And always there is a conversion that is possible from S parameters to Z, Y or ABCD parameters. So this is a very important aspect. So look at the diagram. Again we have a two-port network. Instead of discussing it in terms of the terminals, let us discuss it in terms of port. We have port 1, port 2. And in port 1, we give the input signal that we call it as incident wave. The port 1 is connected to a device and the device is connected to port 2. So there are two junctions that are formed in this diagram. One is from port 1 to device, another one is from device to port 2. If the input signal, what we call it as incident signal, incident wave, because of impedance mismatch are allowed to get reflected back. in the same direction. Some of the energy is allowed to get reflected back in the same port. And coming to the next analysis, the device is connected to port 2. Again we have a transmitted signal because the incident wave is given to the device. So that signal is connected to the load, and because of the impedance mismatch that is between the port 2 and the load is connected to port 2. There is a reflected signal, and the energy that is delivered from the device to port 2 is transmitted wave. So now we will discuss that the transmitted and the reflected wave will have changed in amplitude and phase from the incident wave. Generally, the transmitted and the reflected wave will be at the same frequency as the incident wave. So now, using the scattering parameter methodology, we are trying to characterize the network by observing transmitted and reflected power waves. Generally, we will use only amplitude value. So this is a network of our interest. Port 1 of this 2-port network is connected to a voltage source, and that is connected to a impedance, source impedance ZS, and the incident wave is represented as B1. The corresponding reflected wave is represented as B1, which is in opposite direction to the incident wave. And port 2 is connected to the load impedance, and the transmitted wave is represented as A2, and the reflected wave is represented as B2, which is again opposite in its directions. So, in nutshell, the incident waves are A1 and A2. The reflected waves are B1 and B2 at their respective port 1 and port 2. So how the analysis is made using vector network analyzer. Vector network analyzer is a device that is used to measure the S parameters for any number of ports. So here the picture shows a desktop model of vector network analyzer, and it is restricted with the frequency range. We have port 1 and port 2. This is a calibrating kit that is used to avoid the present or already existing standing waves in the device. And assume that this is port 1, this is port 2. So based on the reflections that are produced in the device, the wave amplitude is observed in the monitor. So this is the working methodology of a vector network analyzer for measuring S parameters. So with this, the analysis of a 2-port network is completed. Thank you so much.